Hello, and welcome to this online lecture. My name is Patty Kokish, and I teach Math 136 both online and in person in the Northwest region. Today we are going to be covering topics from week 14. This is your last week of new material for this class. Week 15 just requires you to do a final exam review homework, and then week 16 is open for you to actually take your final exam. So I will be doing one last online session for you guys for week 15. I'll do some kind of cumulative final exam review that covers off on some of the things you see in the final exam homework. It will just be a bunch of different problems. I'll probably pick the things that I think are most difficult for students. So please tune in for that if you can. That will be next Monday, which is December 8th, from 3 to 4:30 in Central Time, which is 4 to 5:30 Eastern Time. So what we're going to start with is section 12.1, and I say start with, but it's the only section that we have for this week. We're going to talk about systems of linear equations, and we're going to solve them using substitution and elimination. Now, this is something you're probably very familiar with if you're in this class, which is solving equations that have an x and a y in them. If you're given two equations with two variables, that's something that you should be used to. We're going to go through several examples first of problems like that, and then what we're going to do is we're just going to add one more equation and one more variable. So what we'll end with today is three equations with three variables, x, y, and z, where you have to solve for all of them. We're going to use many of the same methods that we used for solving two equations with two variables, but it can be a little trickier and it takes a little bit of getting used to. So the first thing I want to go through is a couple of different ways that we can have a solution or maybe no solution at all for linear equations. So the first thing is that if we graph two linear equations, each with an x and a y, if the lines intersect, then the system of equation has one solution given by the point of intersection. This system is called consistent, and the equations are called independent. So if you look at this picture here, the pink and the blue lines are clearly intersecting at this point here, this black dot that we have that's labeled with solution. And so this is just intersecting lines. System has one solution. So it only has one solution because these lines are going to continue on indefinitely to negative infinity and positive infinity. They will never hit one another again because lines are straight. They're not going to curve back around towards one another. So we just have this one solution right here. So that's called a consistent system. Equations are independent. Okay, the next option that we have is something where we might have lines that are parallel. So then the system of equations is said to have no solution at all because the lines never intersect. So if you have two parallel lines, then you're going to have an inconsistent system. So far we had a consistent system where we just have one solution. This is kind of the most typical. And then we have an inconsistent system where we have parallel lines, no solution. So if you look at these pink and blue lines here, they don't intersect with one another ever, and again, they're going to continue on forever in both directions. They're never going to turn because they're straight lines, so we're never going to have an intersection. Now, if the lines are coincident, then the system of equations has infinitely many solutions, which is represented by the totality of points on the line. So this system is consistent, just like the first one was, but the equations are called dependent instead of independent. This is not as typical as having independent equations, but it's definitely possible. So if you look at this, it's kind of hard to tell, but the whole idea was we had our pink and our blue lines. Now our pink and our blue line are right on top of one another, so they've created kind of this purpley line here. So this is an example where we have basically two lines that might look different initially to the eye, but when we actually get down to simplifying our equations and solving them, they're actually the same line. So again, just to wrap up, we have three different things that can happen. We can have a consistent system where the equations are independent, which is where we have one solution, and this is the one that's most typical. We can have an inconsistent system where we have no solutions at all because we have parallel lines, or we can have a consistent system that has solutions where the equations are dependent. So all of the solutions are on that line. It's going to have infinitely many solutions. Okay, so let's start by graphing a system of linear equations. So hopefully you remember a little bit about graphing. We're not reviewing too much of it here. This is not the best way to solve a linear equation. We're going to do a couple of examples just so you can visually see, for those of you who are visual learners, what exactly this looks like when we're picturing it. But typically we're going to use either substitution or elimination if we want to actually solve. But let's start by graphing. So let's say we have 2x plus 3y equals negative 3. And we have 4x minus y equals 3. Now, what we'd like to do is we'd like to identify what type of system we have and maybe see if we can estimate where the point might be. So the first thing you want to do is go ahead and graph these. Now you have several options. You could graph using x and y intercepts. Kind of the most typical type of graphing, if you remember though from when we graphed lines, would be to put it in the form y equals mx plus b. Now, if you remember y equals mx plus b, that's slope-intercept form. M is going to be your slope, and b is going to be your y-intercept. So if we put our first equation into slope-intercept form, in order to do that, we want to get y by itself. So we would subtract 2x from both sides. Whatever you do to the left, you have to do to the right. So we'd move the 2x over here, make it negative. And then we divide everything by 3. And when we do that, what would happen is we'd be left with y equals negative 2 over 3x minus 1. Now, be careful when you divide by 3, you have to remember to divide everything by 3. So you're going to divide your negative 2x by 3 so that you get this piece right here, and you're going to divide your negative 3 by 3 so you get the negative 1 here. Okay, now to do this other one, this might be a little easier because we don't have a number in front of our y, but you have a couple of options. You could either add y to both sides and then subtract 3, or you could subtract 4x from both sides and then divide by a negative 1 or multiply by negative 1. So it doesn't really matter which way you like to think about it. I would probably subtract 4x from both sides. So we'd get negative y equals negative 4x plus 3. And then in order to get rid of this negative or negative 1 in front of your y, you either multiply or divide by a negative 1 really. So you're just left with y equals positive 4x minus 3. So the signs flip. So if we want to graph this, if you recall, the red line, let's look at that one first. That one's going to have a y-intercept of negative 3, which is right down here, and then it has a slope of 4. So that means that we go up 4, so we go from our y-intercept of negative 3, we go up 1, 2, 3, 4, and then we go to the right 1, because 4 is the same thing as 4 over 1. So that gives us our line right there. And then for the blue, we have negative 1 as our y-intercept, so we start there. And then we have a slope of negative 2/3. So we have a couple of options. First option would be to go down 2 and then right 3. And we end up somewhere in this quadrant over here, somewhere around here. Well, let's see, down to right 3. So we end up right here. We could also go up 2 and left 3. That would work as well. So we end up with a point somewhere around here. Either way works. So you can see that there definitely is some solution. This is a consistent, independent type of problem. The two lines intersect at the point 3/7, negative 9/7. Now we can't really tell exactly what this point is going to be just by looking at it. So this is where we get into the actual algebra part, which we're going to cover off on later. But you could kind of estimate it. It's somewhere around, I don't know, 1/2, maybe a negative 1. Those are pretty close. But the actual solution is 3/7, negative 9/7. All right, let's do one other like this. So let's say we want to graph the system 2x plus y equals 5 and negative 4x plus 6y equals 12. So again, we're going to use the same approach. We're going to put these both into slope-intercept form, which, if you recall, is y equals mx plus b, where m is the slope and b is the y-intercept. So for the first one, we would just subtract 2x from both sides. This one's a really nice one because we already just have positive y on the left-hand side by itself. It doesn't have a number in front of it. So if we just subtract 2x from both sides, we're left with y equals negative 2x plus 5. And then this bottom equation, it's a little nastier looking. We need to add 4x to both sides because if you notice, it's negative 4x. In order to get it on the other side, we're going to have to add 4x to both sides. So we'd add 4x and then divide by 6. And again, you have to divide everything by 6. not just the 4x, you also have to divide the 12. So if you do that, you get y equals 2/3. That's simplified because it was 4/6 plus 2, because 12 divided by 6 is going to give you 2. Now, again, we just want to figure out what type of system we have. Does this have a real solution, infinitely many solutions, no solutions at all? And if you think about graphing these for a minute, we're going to have, let's see, we have our blue line. We're going to have a y-intercept of 5, which is right here, and we're going to have a slope of -2, which is the same thing as -2/1. So if we go down 2 and right 1, or up 2 and left 1, that will give us another point on our line. So down 2 and right 1 would be somewhere around here, up to left 1, that would be somewhere over here. And then this one, we have, for our pink line, we have a y-intercept of +2, so that's going to be right here, and then our slope is 2/3. So if we go up 2 and right 3, that would work, or we could go down 2 and left 3. And you can see again that this is a consistent system with independent equations because we have exactly one solution. What you'll notice is if you end up with something where you have the same slope here, then you know that you might have something where your lines are parallel or right on top of one another, so that you have let's see, let's go back to where that was. The inconsistent system for the parallel lines, or you could have the consistent dependent, where you have the same slope. Now, if you have the consistent dependent, that means that you have the same slope and the same y-intercept. If you have inconsistent systems, that would mean that you would have the same slope. So, for example, you could have -2 here and -2 here, but different y-intercepts. So that would indicate that you have parallel lines. Lines are parallel if they have the same slope. And this one, again, we can't tell exactly where it is, but it looks like it's somewhere around 1/3. The exact value we would have to get using some of the techniques we're going to talk about in just a minute. And in our case, it ends up being 9/8 and 11/4. Okay, so let's move on to actually solving systems of equations by substitution, which is a very important technique. We're also going to use elimination, which I think is a little easier, but it doesn't really matter. If you like substitution more than elimination, then that's fine. Typically, when we get to the 3 equation ones, we are going to use elimination for those. Okay, so let's say we have something like this. 2x plus 3y equals -3, and 4x minus y equals 3. So step 1 is going to be to pick one of the equations and solve for one of the variables in terms of the other. So it doesn't matter which equation you pick or which variable you pick. You do want to make your life as easy as you can. So in our case, it's going to be easiest to get this y by itself because everything else has some kind of a number attached in front of it. So that means we have to divide, and we could end up with fractions possibly. So if we subtract 4x from both sides, divide by -1, which you kind of already talked about previously, we end up with y equals 4x minus 3. Now again, this is solving systems of equations by substitution. If you're used to using elimination, which I think is a little easier, and you want to do it that way to confirm that this ends up being the same solution, then that's completely fine. Either way works. But with substitution, the very first step is to always get one of the equations so that you have one of the variables by itself. So we have y equals 4x minus 3. Now step 2 is to substitute the result into the remaining equation. So since we used the second equation for this first step, we're going to now use the first equation since we didn't use that yet. Now if you notice, we have 2x plus 3y equals -3. And if you look at what we have for step 1, we know that y equals 4x minus 3. So what we're going to do is we're going to say that since y is equal to 4x minus 3, instead of using y in my first equation, I can just use 4x minus 3. So what I'm going to do is I'm going to take my first equation, 2x plus 3y equals -3, and I'm going to substitute 4x minus 3 in for y. So I have 2x plus 3 times 4x minus 3 equals -3. And then if one equation in one variable results, which it should, we want to solve this equation. Otherwise, we need to repeat steps 1 and 2 until a single equation with one variable remains. So in our case, it looks like what we need to do here is just go ahead and distribute our 3 So we have 2x plus 2x plus 12x minus 9 equals negative 3. We want to solve for x, so go ahead and add 9 to both sides and combine your x's because those are like terms. 2x plus 12x is going to give you 14x. If you add 9 to both sides, you're going to get an equals 6. And then you want to divide both sides by 14. So we get x equals 6/14, which of course reduces, they're both divisible by 2, it reduces to 3/7. Okay, now step 4, once you have one of the variables, use back substitution in order to find the remaining values. So we know that x is equal to x is equal to positive 3/7. So what we're going to do is we're going to use the equation from step 1, which is the easiest one to use. You can use anything though, it really doesn't matter too much. So we're going to take our 3/7 and we're going to plug that in for x. So we know y equals 4 times 3/7 minus 3. And if we do this, you have to remember a little bit about fractions or use your calculator very carefully, and you get y equals negative 9/7. Step 5 is to check the solution that you found. Now, the easiest way to check this is to just plug x and y in to both equations, equation 1 and 2, and make sure that they both work. So we have 2 times 3/7 plus 3 times negative 9/7 equals negative 3. And if we actually simplify this, this one does in fact work out. You get negative 3 equals negative 3. And over here we have 4 times 3/7 minus negative 9/7 equals positive 3. And again, if we simplify this one, it also works. We get 3 equals 3. So our solution, which we'll write as an ordered pair with x comma y, is going to be 3/7 because that's our x value, and negative 9/7, which is our y. Okay, the next thing we want to do is to solve equations using elimination. Now, there's nothing wrong with using just substitution or just elimination. It's really personal preference, but sometimes one way is a little easier than the other. So we have some rules for obtaining an equivalent system of equations. Rule 1 is that you can interchange any two equations of the system. You can multiply or divide each side of an equation by the same non-zero constant. So I think you guys probably know this. If you multiply the left-hand side by 2, that means you have to multiply the right-hand side by 2 as well. You can replace any equation in the system by the sum or difference of that equation and a non-zero multiple of any other equation in the system. So this sounds a little complicated, but in practice, it's actually not too bad. So let's look at an example here. We have 2x plus 3y equals negative 1 and 2x minus y equals 3. Step 1 is to multiply both sides of one or both of the equations by a non-zero constant so that the coefficients of one of the variables are additive inverses. Now, additive inverses, basically what we want them to be is just so that they're going to cancel with one another. So if you think about it, if we had 3y and negative 3y, or 2x and negative 2x, those two things are going to cancel. So that's what we want to have happen. So if we look at our equations, if you don't tend to like dealing with negatives, what you want to do is you want to look for something that already has opposite signs. So if you look at this, we already have a positive 3y in the first equation and a negative y in the second equation. So all we would really need to do is multiply this second equation by 3, because then what's going to happen is we're going to get a negative 3y, which is going to go away. So if we multiply the second equation by 3, and you have to be careful, make sure you do it to both sides. We have 3 times 2x minus y equals 3 times 3. And if you simplify that, you still have 2x plus 3y equals negative 1. That's your first equation. Multiplying the second equation by 3 gives you 6x minus 3y equals 9. And then all you do is just one big addition problem. So 2x plus 6x is going to give you 8x. What you'll notice with the y's is we have a positive 3y and a negative 3y. Those are going to cancel, okay, so we're left with nothing there. And negative 1 and 9, that's going to give you 8, okay. Now you always want to end up with something, when you're solving two equations with two variables, you will always want to end up with something where you just have one variable equals something. So that's kind of the next step would be to just finish this. Divide both sides by 8, so you get x equals 1. Now we use back substitution to basically use the value that we found in step 2, so we found x equals 1, into one of the original equations to find the remaining variable. Now you can pick either of the originals, it really doesn't matter. It looks like we chose the second one here. So we have 2 times 1, because we had 2 times x, minus y equals 3. And if you solve this, subtract 2 from both sides, so you get negative y equals 1. Divide both sides by negative 1, so you get y equals negative 1. And again, just like the last one, you want to check the solution that you found. So you want to make sure that you plug 1 in for x, negative 1 in for y, and make sure that both equations work. So in our case, we have 2 times 1 plus 3 times negative 1 equals negative 1, and that is in fact true. We have 2 minus 3, that gives us negative 1 equals negative 1, so that one is good. And then for the second equation, we have 2 times 1, that gives us 2, minus negative 1 turns into plus 1, so we have 2 plus 1. We know that 2 plus 1 is 3, so that one works as well. So we want to write our solution as an ordered pair again, x comma y. So in our case, we have x equals 1 and y equals negative 1. So we have 1, negative 1 as our solution. Okay, movie theater ticket sales. So this is kind of an applied version of this same type of problem. So a movie theater sells tickets for $8 each, with seniors receiving a discount of $2. One evening, the theater took in $3,580 in revenue. X is going to represent the number of tickets sold at $8, and Y is going to represent the number of tickets sold at the discounted price of $6. What we'd like to do is we'd like to write an equation that relates these variables. So if you think about it, if you take the $8 times the number of tickets that they sold and add the $6 times the number of tickets that they sold at $6, then we should get $35.80. So this is going to be our first equation. 8x plus 6y equals $35.80, because we have $8 times the number of $8 tickets sold plus $6 times the number of $6 tickets sold. And that's going to give us our total revenue. So let's suppose that we also know that 525 tickets were sold. We want to write another equation that relates x and y. So if you think about this for a minute, we know that x plus y, that's going to give us the total number of tickets that we sold, because it's going to give us our $8 tickets plus our $6 tickets. So we know that together those have to equal 525 if 525 tickets were sold. So now we have our 8x plus 6y equals 3580 and our x plus y equals 525. And we want to solve them in some way. Now we used elimination, it looks like. So in order to do that, we multiply the second equation by negative 6 so that we have a 6y and a negative 6y, which will then cancel. So if you multiply the second equation by negative 6, you're left with negative 6x minus 6y equals negative 3150. You still have this same first equation, and now we just add those together. 8x minus 6x is going to give you 2x. The y's cancel, just like we'd like them to. And this 3580 minus 3150 becomes 430. Then we divide both sides by 2, so we get x equals 215. Now we know that since x plus y is 525, that y is just going to be 525 minus whatever value we have for x. So in our case, since x is 215, y is going to be 525 minus 215, which actually gives us 310. So what that tells us is that 215 non-discounted tickets, those are the $8 tickets, were sold, and 310 senior discount tickets were sold. Okay. Let's now identify some inconsistent systems of equations containing two variables. So let's say we have something like this, x minus 3y equals 2, and negative 2x plus 6y equals 1. Now it looks like what we're going to do is use substitution. So we're going to solve our first equation for x by adding 3y to both sides. Now there's nothing wrong with doing this a different way. You could use elimination, or you could solve for another variable. It's really up to you. There are a million possible ways for solving these equations, but the easiest thing, since x is kind of already by itself, is maybe to go ahead and just solve for it. So we add 3y to both sides, so we get x equals 3y plus 2. And then we're going to use substitutions. We're going to take our second equation and we're going to plug in 3y plus 2 wherever we see an x. So we have negative 2 times x, which becomes negative 2 times 3y plus 2, plus 6y equals 1. We go ahead and distribute carefully. We get negative 6y minus 4 plus 6y equals 1. And then if you think about it, negative 6y plus 6y is just going to be 0. So what we're left with is negative 4 equals 1. Now, -4 is not equal to 1. We all know this. So since the statement is false, we conclude that there is no solution. So we can say that the system is going to be inconsistent. And if you think about what we know about inconsistent systems, these are going to be parallel lines. So they're lines with the same slope but different y-intercepts. Okay, now let's express the solution of a system of dependent equations that contains two variables. So we've talked about independent equations a couple of times now, but now let's do some dependent equations. So let's say we have x minus 3y equals 2 and -2x plus 6y equals -4. We're going to do the same thing that we did last time, add 3y to both sides. So we get x equals 3y plus 2. And then we use substitution, so we have -2 times 3y plus 2 plus 6y equals -4. We use our distributive property, so we get -6y minus 4 plus 6y equals -4. This one's very similar to the last problem, except we have some different constants. -6y and +6y are going to cancel, and we're left with -4 equals -4. Now, this statement is true. We know that -4 is indeed equal to -4, but we don't have any variables. So what this means when we're left with some true statement like 1 equals 1 or 10 equals 10 or 100 equals 100, the two equations are going to be equivalent, so the equations are actually dependent. So if you think about that, we actually just have a line here. Now the way that we write our solution is in set builder notation. We say it's all x's and y's, so x comma y, such that x is equal to 3y plus 2. And that's what we got for our first equation here. It is important to note that you can express any variable in terms of the other. So if you wanted to instead have y equals let's see, what would it be? X minus 2 over 3, that would be fine as well. You just want to make your life as easy as possible. So if you do end up with dependent equations, what you need to do is you need to get one variable by itself in either of the equations, and then that's going to be this part that comes after this pipe right here. Okay, let's now move on to kind of the new thing. I hope that other stuff was review. It should have been. Now what we want to do is we're going to add an extra equation, add an extra variable. So we want to solve systems of 3 equations containing 3 variables. So I have some methodology here for us. Now there are different ways of approaching this, but this way, if you're stuck, tends to work. So there are many different ways to solve these types of problems. Elimination method is typically the easiest. You're going to take them in pairs. So you're never going to deal with all 3 equations at once. You're going to do 2 pairs of 2, okay? And you have to eliminate the same variable each time. In addition to that, you need to use each of the 3 equations at least once. So if you use the first 2 equations for your first pair, then you have to use that 3rd equation as part of your next pairing. Then you'll be left with 2 equations with 2 variables, which you should now be very familiar with. And at that point, you can use any approach that you'd like. Elimination or substitution are normally your best bets. And then, of course, you want to go ahead and check by substituting into all of the original equations. So what we want to do, we visualized some of the things where we had 2 variables. We want to now visualize some of these ones where we have 3. So if you look at these planes, we have a blue, kind of a pink or peach kind of color, salmon maybe, and purple. And if you look at this, this is a consistent system that has one solution. So if you look at where all of these planes intersect, we have exactly one solution there. But if we take a look at something else, we have kind of a specific thing happen. This is also a consistent system, but this has an infinite number of solutions. So if you look at this black line here, these are all solutions. Okay, so this is an infinite number of solutions, much like our dependent equation that we had for our 2. And then this right here, this is an inconsistent system. So if you look, there's no way where these, or no place at which these all intersect, the blue, the purple, and this kind of pink color. Now, the blue and the purple intersect, the blue and the pink and the purple, they all intersect with one another, but they never all intersect in one place. So this is kind of a no solution type of problem. This is an inconsistent system. Okay, so what we want to do here is use the method of elimination in order to solve our system of equations. So we have 2x plus y plus z equals 4, and we have negative 3x plus 2y minus 2z equals negative 10, and we have x minus 2y plus 3z equals 7. So what we want to do is we just want to pull out two of the equations that look like they fit together kind of nicely and eliminate some variables. So if you look at the first and the third equation, if you look at the x value, we have a 2x and an x. It would be pretty easy to get rid of that. So again, there's no really right or wrong way to go about this. You could easily decide to eliminate something else. But let's say we want to eliminate x and we want to use the first and the third equation. If we keep the first equation how it is, we keep it as 2x plus y plus z equals 4, and we multiply the last equation by negative 2, then we have to multiply both sides by negative 2. So we have negative 2 times our third equation, which was x minus 2y plus 3z equals negative 2 times 7. We go ahead and distribute the negative 2 through. So we have our original equation, our first equation, and our new third equation, which is now negative 2x plus 4y minus 6z equals negative 14. We go ahead and add those together. The x's are going to cancel, which is the whole goal. We want something to cancel. It doesn't matter what cancels, but we need something to cancel. So in this case, we've canceled x. So if we add y plus 4y, we're going to get 5y. If we take z minus 6z, we're going to get negative 5z. And if we have 4 minus 14, we get negative 10. And now what we need to do is we need to pick another pair. Now what has to happen is you have to use this second equation because we only use the first and the third for that first part. So since we didn't use the second equation yet, we're stuck with that one. So we have to use the second equation. Now you can either use the first or the third. So we're going to take our second equation, and it'll be a little easier if we use our third equation, because what we want to do is we want to eliminate the same variable that we eliminated the first time. So if you look back at what we did over here, we eliminated x. So what we want to do again is, eliminate x. So if we look at our second and our third equation, the originals, if we just take our third equation and we multiply everything by 3, then our x's are going to cancel, which is exactly what we want. So we have our second equation, negative 3x plus 2y minus 2z equals negative 10. And we have our third equation, which we now want to multiply by 3. So we have 3 times x minus 2y plus 3z equals 3 times 7. We distribute and you get 3x minus 6y plus 9z equals 21. Add those together. So we have negative 4y plus 7z equals 11. And then what we want to do is we want to take our two new equations that we have. We have 5y minus 5z equals negative 10 and negative 4y, plus 7z equals 11. And we want to put those together. So in order to do that, we're going to multiply our first equation by 4 and our second equation by 5. We go ahead and distribute. So we have 20y minus 20z equals negative 40. And we have negative 20y plus 35z equals 55. Now at this point, this should look pretty familiar. Really all you're doing is you're just solving two equations with two variables. You could use substitution or elimination at this point. It doesn't really matter. We add these two together, and we get 15z equals 15. So we're left with z equals 1. Now what we do is we use one of the two equations that we had originally created here. We had 5y minus 5z equals negative 10. We're going to use that to solve for the other variable. So we have 5y minus 5 times 1, which was z, equals negative 10. And if we solve that, we get y equals negative 1. And then at this point, once you have two of your variables, it doesn't matter which two, you can use any of the originals to solve for that last one. So we're going to use this third original equation, x minus 2y plus 3z equals 7. We substitute negative 1 in for y and 1 in for z. So we have x minus 2 times negative 1 plus 3 equals 7. And we get x equals 2. So the way that we want to write this is 2, comma, negative 1, comma, 1. So when we have three coordinates, we write it as x, comma, y, comma, z. Now, a good thing to do would be to check this. You check it the exact same way as the others, except it just takes a little more time because you have a little bit extra. You have an extra variable there, an extra equation. So if you want to check this one, you're going to take 2, plug it in for x, y, plug it in for, or sorry, -1, plug it in for y, and 1, plug it in for z, and then you do that for each of these equations and make sure that they all work. Okay, now we want to identify inconsistent systems of equations containing 3 variables. So let's say we have something like this: 2x minus 3y minus z equals 0, -x plus 2y plus z equals 5, and 3x minus 4y minus z equals 1. So we want to use kind of the same tactic that we used for the last one. If you look at equations 1 and 2, it's going to be pretty easy to eliminate your x's by multiplying your second equation by 2. So we take the second equation and we multiply by 2, and we're left with -2x plus 4y plus 2z equals 10. And we have our same first original equation. We add them together and we get y plus z equals 10. And then since we didn't use our third equation, we need to use that one, which is 3x minus 4y minus z equals 1. That one's going to stay intact. And we're going to take this second equation and multiply by 3 so that we can eliminate this x. And once we do some distributing and combining, we should get 2y plus 2z equals 16. So we take our y plus z equals 10 and our 2y plus 2z equals 16, and we combine them by multiplying the top equation by -2. So we have -2y minus 2z equals -20. Add it together, and -2y minus 2z plus 2y plus 2z, that's just going to be 0, and -20 plus 16 is going to be -4. So we get 0 equals -4. Now we know that 0 is not equal to -4, so this statement is a false one. So we would conclude that there is no solution. So we can say that the system is going to be inconsistent. Okay. Now we want to express the solution of a system of dependent equations that contains 3 variables. So we have x plus y plus 2z equals 1. 2x minus y plus z equals 2, and 4x plus y plus 5z equals 4. So if you look, let's see, what should we do here? We're going to take this first equation and multiply by -2 so that we're going to get the x's to cancel with the first and the third. So we're left with -2x minus 2y minus 4z equals -2. And we have our second equation, which is 2x minus y plus z equals 2. Add those together, and -2y minus y is going to give you -3y. -4z plus z is going to give you -3z, and -2 plus 2 is going to give you 0. So you have -3y minus 3z equals 0. Now we need to use that third equation since we haven't used it yet. If we take the third equation and the first equation, and we take this first equation and multiply by -4, then our x's are going to cancel. So if we multiply this first equation by -4, we're going to be left with -4x minus 4y minus 8z equals -4, and we add it to our third equation. So we're left with -3y minus 3z equals 0. Now if we take these two things and we put them together, what we get is 0 equals 0. Now that statement is true. So unlike the last one, we got 0 equals -4. I think that one didn't make any sense, but 0 equals 0 is true. But we don't have any variables. So that means that the equations are going to be dependent on one another. So we're going to have, we're going to use basically this equation that we have here, this -3y minus 3z equals 0, and we're going to solve for one of the variables. It does not matter which variable you solve for. But if we solve for y, so we're going to add 3z to both sides, divide by -3. We're going to get y equals -z. And now that we have that, what we would want to do is we want to go back and plug it back into one of our original equations. In this case, let's see, we'll use our first equation. So if you take our first equation and we solve for x, we're going to have x equals -y minus 2z plus 1. By subtracting y and subtracting 2z from both sides. So what we would end up with is, since we know that y is equal to -z, what we're going to do is we're going to plug -z in everywhere we see a y. So we have x equals negative negative z minus 2z plus 1. Now, negative negative z is just going to be a positive z. So we have z minus 2z plus 1, which if we simplify that, we get negative z plus 1. So we have y equals negative z, and now we have x equals negative z plus 1. The entire goal is for you to get basically two variables, any two, it could be x, y, or z, by itself, and you should just have one variable left on the right-hand side. So in order to write our solution, we write it in set builder notation. We have all x, y's, and z's such that x is equal to negative z plus 1, y is equal to negative z, and z is any real number. So the whole idea is we could make z be anything that we want, and then we could find x and y by plugging that number in for z. Now there are certainly other ways to do this. You could have x be any real number and have y and z over here. It doesn't really matter either way. So if you have any questions, this is my email address, pseberger@ivtech.edu. Please feel free to email me any questions that you have from 12-1. And please join next week. We will be doing a nice review of a lot of the material from this last half. I'll have to go back and see. I don't recall if there are questions from the first half of class as well. But we will definitely cover off on the more difficult material that you've covered so far. If you have anything in particular that you would like me to cover in the online lecture, please feel free to email me with your suggestions, and I will definitely take that into account when I create my presentation.